Hello, my name is Abdulatif Ogudipe, a second-year doctoral student at Laboratory Automatic Mechanical Industrial at UMER, Université Polytechnique Hauts-de-France, and I will be making a presentation on our conference paper titled The Coupled Initialization-Based Distributed Tube Model Predictive Control for Multi-Robot System Coordination. And these are my supervisors and thesis director. To begin, this will be the outline of my presentation, and we'll take you through the motivation and challenges, the problem formulation, the proposed algorithm, the simulation result and experimental validation, discussion, conclusion, and future work. Why multi-agent coordination? Multi-agent system is a group of agents that are trying to achieve a global task in an environment, in a shared environment. An agent is anything that has the ability to percept its environment, being able to compute, be able to take an action autonomously, and be able to communicate. The application of coordination of multi-agent system can be found in autonomous exploration, environmental monitoring, inspection of hazardous region by robots where we don't want humans to go, then logistic activities by vehicles in the warehouse environment or inaccessible places. To ensure proper coordination and safety of multi-agent system, there needs to be control algorithms that will be used to ensure the proper coordination. Out of the existing coordination that's available, model predictive control has been one of the popular and most effective one due to its ability to be able to predict the future state of a model over a finite horizon into the future, and while considering the constraints to produce constraint action produce the control action. And when multi-agent system scales up, the distributed or decentralized MPC enables parallelized optimization-based decision in multi-agent system, whereby each agent can be able to solve their problem in parallel instead of considering it as a central coordination, which will be heavily intensive. In the existing distributed MPC method, it has been observed that most times it is being formulated as single stage DMPC, and in the sense that the agent dynamic, the goal state, the constraints are all put in an optimization problem to give contraction. This has led to practical challenges in practical scenario, such as communication limitations, infeasibility under disturbance, long travel times, and all this leads to inefficient real-time performance, which makes it difficult to use MPC in practical scenarios. Before I delve into my work, I will just the work that was done. I would like to take you through some existing MPC strategies for multi-robot coordination. We have the earlier stage of MPC starting with the works of Main and Rollins, where they worked on the centralized MPC, which has a global optimal but blows up with field size, and also have the problem of single point of failure. In the recent time, we've had tube-based DMPC and parallelized robust DMPC with reference, in which disturbance robustness is being inserted into the DMPC through invariant tubes, and the distributed nature is also used for multi-robot coordination. But for a very close reference to our work is the parallelized robust DMPC by weight, which needs inner iteration and costly offline reference pre-computation when compared with our work. Similarly, it's very important because the proposed method is under the algorithm of hierarchical AMPC, and whereby you have an upper layer guiding lower layer. But we didn't see, to the best knowledge of the authors, there has been no work with respect to non-illuminate to DMSC. And these are like the kind of comparison between different MPC compared to what our work is. And we can say that our proposed DI-DTMPC actually perform better based on the metrics, and that's what I'll be making presentation on. To present since we are focusing on a particular aspect of multi-agent system, which is the multi-robot system, and to specifically talk about the model, we'll be looking at the non-autonomic robot, which motion is a bit difficult to plan because of its non-lateral motion. It can only move in one direction, and it's used pure rolling to make turning and all. And this is the description of the system, and we have the discrete representation of the model when considering disturbance, which is the force in DIK, and when considering nominal disturbance, which is in the second, which will be used for MPC formulation. And in the concept of multi-robot system coordination, we have some constraints which is very important for us to introduce. One is the input constraint, the other is the local constraint, and the last is the coupled constraint. Input constraint is the physical limit on linear and angular velocity, while local constraint is the avoiding of static obstacles and maintaining safety margin. And the coupled constraint, which is like the most difficult one for robots to solve, is the collision avoidance between different robots because they share same states together. So, and this how we represented the formulated the constraints as seen. Now, the key idea of this approach is to split this problem into two stages. Like it was said, the single stage DMPC is to just undo everything as once, as mentioned in the DMPC. Then for the proposed two-stage DMPC, we have stage one, simple uncoupled problem, goal directed, and we have the stage two being utilizing the feasible initial trajectory being given by the stage one to be able to simplify the robust problem in the second stage, and also consider the exchange of data with the neighbors. And with this, it enforces collision avoidance. And this is where the term decoupled initialization in the topic comes in, because the decoupled initialization from the start stage one is able to remove the hardest coupling from the costly inner solve. And the objective of the robot is to start from a particular position and end while avoiding static obstacle, avoiding other robots, respecting input limit and tolerating bounded. And to give a kind of block diagram to be able to see how the process goes is, the stage one starts creating the U-worm, which is being fed to the stage two, and the nominal control is being gotten from the stage two full MPC, which is now being utilized by the auxiliary control to ensure that the actual state is within the limit of the nominal state of the robot, and is being applied, and it's at the stage two that we have the neighbors prediction. And this is what this block. In order to be able to put some technical information about the robustness, we use the concept of tube MPC, whereby the nominal trajectory is within an RPI tube, and the actual trajectory is ensured that it's being enforced within the range of the tube, not leaving the tube of the nominal trajectory. And the RPI set being used is being represented with HI, which is absorbing all the disturbance DI in the actual system. Also, for the respect of between the actual and the nominal, we need to also do the constraint tightening, which is used later to prove the constraint satisfaction of the MPC. Similarly, the consistency constraint is what links the stage 2 to the stage 1 reference to ensure that the stage 2 trajectory tracks the stage 1, which is the initially feasible solution for it to be able to solve the stage 2 problem accordingly. So this is where the coupling major usually happen. So other ingredients of the formalized problem is the stage cost, which is the quadratic regulation to go, which has to reduce based on the positive definite matrices being used on the state and the being used to penalize the state and the control in the stage cost. And we have the terminal cost, which is used for the stability argument to ensure that this decreases. And for the distributed interaction, like we said, each robot needs only its own state and neighbors warm trajectory to be able to coordinate itself in the environment. To put the stage 1 and stage 2 in perspective, this is the optimization problem as formulated and the constraints subjected. In stage 1, one thing that is very important to note is the tightening margin delta, which leaves room for the stage 2, is one of the designed parameter to ensure that what we have in stage 1, there is some space for the stage 2 to be able to modify the trajectory, and whereas the stage 2 has the full optimization, including the tube anchor, the nominal, following the nominal trajectory, the tightened input, as earlier mentioned, the consistency constraints, the terminal set, and at the end of the day, the applied input of the nominal input from the controller is being used with the auxiliary controller to ensure that the actual state maintains within the range of the nominal state due to disturbances. So just to show you the execution timeline, as earlier shared, we exchange, the stage 2 is done and apply, and this is the flow chart of how everything is being done. And at the end of the day, we have the decoupled initialization. Stage 1 is independent per robot, and company enters on the stage 2. The theoretical guarantee is very important. There are majorly three, which here we are talking about the recursive feasibility and the robustic asymptotically, and this theorem was formulated under unnecessary assumption. The problem stage problem is recursively feasible, and the closed loop is robustly asymptotically stable with respect to the goal. And the concept of the recursive feasibility is to choose a shifted candidate solution built from previous optimal plus the terminal controller, which is always feasible, and the tube membership re-anchors the nominal state at the actual state at each step to ensure this is being transferred at every time step. And the significance of this is that the controller never gets stuck. A feasible plan exists at all times despite disturbance and coupling. So which simply implify feasibility once, feasibility forever. For the robustic asymptotic stability, we utilize the Lyapunov argument of robustness, whereby we have to ensure that we choose the cost function of the second stage as our Lyapunov function, and we prove that between a previous time step and the other step there is a reduction, which shows that the robot is going towards the neighborhood of the goal. And this is just an illustration of this. So for the validation with this simulation, and this is the scenario considered and the tools used, and for the experimental validation we utilize 3 mobile robots, and these are the software communication and the communication architecture. For the results, for the simulation, we have our warm start for a particular extreme case, which is the antipodal position of robots, whereby you see that the trajectory of the robot crosses, and we have the warm starts like this at the stage 1, and the stage 2, which is deforming the warm start to be able to avoid all other constraints like collision avoidance is done. And during the whole simulation, the safety margins respected with positive values at all times. As part of the validation of the proposed algorithm, we compare with a single stage method, and we have the comparison to have more travel time. As you can see that the robot has gotten to the goal in the proposed scheme when the classical scheme is still trying to navigate. And similarly, we add an average of over several trying, we have an average of 10 to 15% better initialization compared to the single stage, and it's being validated with the mobile robots in the experiments shown on the screen. All right. Similarly, the most close reference, we compared some case scenario, the collision scenario, with the PDMPC, which has a offline reference, whereas this our own proposed stage has a online reference. So from the method we add that the two-stage MPC have a better cost, even though it's 2 MPL per step, but due to the formulation, there is due to formulation and better guess and fewer activities, there's low system level computational budget, so lower closed loop cost and drastically small offline cost than predefined reference scheme is being observed from that result. So in conclusion, we're able to achieve this benefit from the proposed stage with better feasibility and few local minima and proven safety and robustness. The limitation is when the neighbors are too much to generally, still the neighbor communications could be more so much and could affect the algorithm. Then the tuning of parameters and the two NLP per step, even though they are easy to solve. And we are looking at future directions in handling disturbance rejection observer, dynamic obstacle, and time varying topology. So in summary, this was like the contribution of this work as part of my thesis work, and these are the references. And thank you for your attention.